Okay, let's talk next about coordination and anti-coordination games. And those are games that have essentially two solutions or two Nash equilibria. The games that we played so far, they only had one Nash equilibrium, and once the Nash equilibrium was not a problem because the Nash equilibrium was also the social optimum. But once the Nash equilibrium is a little bit of a concern to the players, when the Nash equilibrium, like in the prisoner's dilemma, is not the social optimum. So what types of coordination and anti-coordination games are there? So again, in game theory, we are generally concerned with non-cooperative strategic interactions. And as we said, we distinguish coordination and anti-coordination games. In coordination games, we win together or lose together. And coordination games are known as Battle of Sexes, Stack Hunt, and pure coordination games. So in a coordination games, the objective is that we both try to do the same thing, more or less, and if we coordinate ourselves such that we end up doing the same strategy, then we both win. In anti-coordination games, we win when we do different things. And in anti-coordination games, we have somewhat embedded the idea of zero-sum games. So one wins, the other one loses. Okay, so coordination games are known as Battle of Sexes or Stack Hunt or pure coordination games. They're a little bit different and we will go over them now. And in anti-coordination games, they are typically known as hawk-dove games. Okay, so let's start with coordination games and start with the Battle of Sexes game. So in a Battle of Sexes games, like all coordination games, there are two Nash equilibria. In this case, there are stadium, and opera. And so let's just play it quickly. So we have two players, he and she, and they have two strategies. They could either go to the stadium or to the opera. So if he thinks that she goes to the stadium, he could go to the stadium or to the opera. And if he goes to the opera, he gets -1, but if he goes to the stadium, he gets 2. So going to the stadium would be better, because 2 is better than 1. If he thinks she goes to the opera, he could go to the stadium and get 0, or go to the opera and get 1. So now we can see that he does not have a dominant strategy. What he does really depends on what he thinks where she's going, but no strategy is dominant. So what about she? If she thinks that he goes to the stadium, she could go to the stadium and get 1, which is better than going to the opera and getting -1. And if she thinks he goes to the opera, she could go to the stadium and get 0, or go to the opera and get 2. So neither she has a dominant strategy, but now we see we have two Nash equilibria. We have stadium, and opera. And both of them are a social optimum, because they are both ending up with an aggregate payoff of 3, whereas the other two combinations, stadium opera or opera stadium, they have an aggregate payoff of -1. So in this case, we could say, no, that's great, the players find their social optimum. So stadium is a social optimum and a Nash equilibrium, and opera is a Nash equilibrium and a social optimum, so that's good. But the interesting question is, which of the two equilibria is likely to emerge? So now we can introduce some additional thoughts, maybe something like cultural norms, like if the society is predominantly male dominated, and we hypothesize that going to the stadium is more of a male thing than of a female thing, then we would say stadium is the more likely outcome. Or if it's a very gender equal country, and they always alternate between what he wants and she wants, let's say, then if we know that the last time they went to the opera together, we would predict that the next time they go out somewhere, they will go to the stadium. But again, what we see here, we have two Nash equilibria. None of the Nash equilibria has a higher aggregate payoff than the other one, but the players have individual preference orders. He obviously prefers the stadium, she would prefer the opera. Okay, so now let's move to the next one and leave the Battle of Sexes game behind us. So the next game is a stack hunt game. So let's also play that quickly. So Hunter 1 and Hunter 2, they can either go for the stack or the hare when they go on a hunt together. If Hunter 1 thinks that Hunter 2 goes for the stack, Hunter 1 is best off by going also for the stack, because the 3 is better than the -1. If Hunter 1 thinks Hunter 2 goes for the hare, Hunter 1 would get -2 if they would go for the stack, and 1 if they also go for the hare. So hare is better than stack. Again, for Hunter 1, we have no dominant strategy. Situation is very similar for Hunter 2. If Hunter 2 thinks that Hunter 1 goes for the stack, then shall Hunter 2 go for the stack and get 3, or go for the hare and get -1, and of course 3 is better than -1. If Hunter 2 thinks Hunter 1 goes for the hare, shall Hunter 2 go for the stack or the hare? Stack would be -2, hare +1, so of course hare is better. So again, we have two Nash equilibria, and in this case stack is actually payoff dominant. That's the social optimum, because the aggregate payoff would be 6. Stack hare -3, hare stack -3, and hare +2. So now we would predict that because stack is the higher payoff for both players, and both prefer stack to hare, that this will also evolve. And later in the lecture we will talk about under which conditions that will actually happen. And I can already tell you at this point, if you just look at this game as it is, and we, let's say, would assume that the society starts out with hare, given the payoffs, stack will not easily evolve. It actually will not evolve. But anyhow, so we know now the game, and we will come back to the to the idiosyncrasies of the stack hunt game again later. But the characteristic of the stack hunt game, as opposed to the previous Battle of Sexes game, is that the players have an individual preference order, which of course the players in the Battle of Sexes game had as well. But there is a social optimum. In a stack hunt game, there's a social optimum, whereas in the Battle of Sexes game, there was no social optimum. So the third coordination game, and the last one that we cover, is a pure coordination game. So let's play that one, and let's just assume that there are two players, he and she, and maybe they lost each other in a shopping mall. So now they can search for each other and they cannot cooperate. So if he thinks that she's in the hat store, shall he go to the hat store or to the shoe store? Of course, he will go to the hat store. So we underscore the 2 because 2 is better than -1. And if he thinks she goes to the shoe store, well, then he will also go to the shoe store because 2 is better than -1. Again, no dominant strategy, like in all coordination games. Likewise, if she thinks he will be in the hat store, she will go to the hat store because 2 is better than -1. And if she thinks he will go to the shoe store, she will go to the shoe store because 2 is better than -1. So again, we have two Nash equilibria, but we have no preference order, and we have no payoff dominance or social optimum, which is better than the other one. In terms of the social optimum, finding each other again in the hat store is as good as finding each other again in the shoe store. Both has an aggregate payoff of 4. Everything else has an aggregate payoff of -2. So no preference order, no payoff dominance, and the question is which is more likely to emerge. And that depends on additional information like the two players, they have a rule that says whenever we get lost, we'll try to look for each other in the stores that are more likely to be liked by her. So that might be maybe the shoe store. Okay, so we can now summarize the characteristics of the 3 coordination games. So all coordination games, they have two Nash equilibria. In the Battle of Sexes game, there is an individual preference order. So he liked the stadium more than she, although he still preferred to be with her in the opera than not being with her, but there's an individual preference order. Likewise, in the stack hunt game, there's an individual preference order. Both players prefer the payoff associated with stack. Only in a pure coordination game, as we just have seen, there is no individual preference order. Pareto superiority. The Battle of Sexes game didn't have a Pareto superiority, and Pareto superiority is just another word for payoff dominance in this context. So no game is payoff dominant, and no equilibrium is, in the Battle of Sexes game, no Nash equilibrium is payoff dominant. So the aggregate payoff for both players is the same in the Battle of Sexes game, although he would prefer to be with her in the stadium, but if he goes with her to the opera, she would win, but he will lose, and the aggregate payoff is the same in stadium as it is in opera. Only the stack hunt game has a payoff dominant or a Pareto superior solution, which was stack. The pure coordination game also did not have any Pareto superiority, because for the two players, finding each other in the shoe store would be as good as finding each other again as in the hat store. So then whenever we deal with a coordination game, we are interested what's the predicted equilibrium, which of the two equilibria is more likely to emerge? Well, maybe in the battle of sexes game, you just will say the last equilibrium is the best predictor for the next equilibrium. In the stack hunt game, it's pretty straightforward. We would say the Pareto superior strategy is most likely to emerge, but as we will see later, this is much easier said than done. And when it comes to pure coordination games, could be additional rules or customs, like the players have already agreed on some mechanism for losing, a mechanism that will take effect once they lose each other. So okay, let's talk next about the hawk-dove game. So hawk-dove games have in common with coordination games that they also have two Nash equilibria. The players also have a rank order, like they have in the Battle of Sexes game or in the Stack Hunt game. And no equilibrium is Pareto superior, like what we have in a pure coordination game. But hawk-dove games, they differ from coordination games in the sense that the players have opposing strategies. That's why we call them anti-coordination games. And once we play that game, on the next slide, we have to introduce agreed upon conventions in advance in order to predict which equilibrium is more likely. So because the hawk-dove game is somewhat confrontational, one of those conventions could be whoever was somewhere first has the right to stay, or might is right. That could be one of those conventions. However, if there are no agreed upon conventions, like when arguing whoever was first here has the right to stay, when the other one says whoever is stronger has the right to say, then we can predict conflict. Okay, so let's make that more concrete by looking at such a typical land tenure example, which is a popular hawk-dove game. So a land tenure game. So we have two players, the peasant and the landlord. And the peasant can either live and work on the land, that would be the hawkish strategy, or the peasant could either live and work elsewhere, that would be the dove strategy. Likewise, the landlord could put the cows on the land or put the cows elsewhere. That would be the dove strategy. So if the peasant thinks that the landlord put the cows on the land, well, then living and working on the land would give the peasant most likely a lot of trouble. The payoff would be -10, whereas if the peasant then goes somewhere else, well, would only get -5, which is still better than having to deal the entire day with a lot of trouble. If the peasant thinks that the landlord puts the cows elsewhere and basically vacates the land, then of course the best strategy for the peasant is to live and work on the land, and then the peasant would get 5 instead of only 7. So the best strategy would be to live and work on the land if the landlord puts the cows elsewhere. So what about the peasant and the landlord? If the landlord thinks the peasant lives and works on the land, shall the landlord put the cows on the land and play hawkish, or put the cows elsewhere? Of course, -5 is better than the -10. Lastly, if the landlord thinks that the peasant lives and works somewhere else, then shall the landlord put the cows on the land and get 5, or put the cows elsewhere and get -7. Of course, 5 is better than the -7. So now we have two Nash equilibria, and we can see, if we look at the aggregate payoff, we can see that nature of a zero-sum game, payoff is 0, under Dove Hawk. So the players play opposite strategies. And if the peasant plays hawk, lives and works on the land, and the landlord plays dove, puts the cow elsewhere, but that's another social optimum. But of course it is a social optimum that involves opposing strategies. If both play hawk, well, that would be really bad. That's the worst. That would be leading to an aggregate payoff of -20. And if they both play dove, so that will leave the land completely unused somehow. That will lead to an aggregate payoff of -14. So the highest possible social optimum is basically a zero-sum game. So again, which of those equilibria, Dove Hawk or Hawk Dove, is more likely to evolve? Well, it depends on the customs that are in place. So if there is an agreed upon convention that whoever is first can stay, then maybe it might be predictable that the peasant actually lives and works on the land, and we will have peasant playing hawk, landlord, and landlord plays dove. But if the convention is whoever is stronger and has more resources, that player calls the shots, then we probably predict that the landlord plays hawk, puts the cows on the land, and the peasant goes somewhere else, plays dove. Okay, so those are basic games, and in the next couple of sections we will elaborate on the various peculiarities of those games a little bit in more detail, and we also introduce some variations. But let's just stop here for now.